Good morning, everybody. Take a seat. Good morning, and welcome back to a new episode of Control Systems 1. We're about to get to the end, and all good things come to an end eventually, but we still got a couple classes. Are we set? So we still got a couple classes to go. We're going to do some fun stuff. But before that, it's time for feedback. So I guess that I hope we have convinced you maybe at this time in the course that feedback is a powerful thing. It's important in general. I mean, of course, in control systems. And while we have been talking about control systems as all these mechanical, electrical, whatever, thermal systems, physical laws and stuff, really control systems applies to everything that is a system, right? And one of the very classes we said, well, systems are basically relationships between input and output signals. So basically anything that we can understand that is a relationship between an input and an output, we can call a system. And even learning, the learning process of people is a system as well. And we can do a control system around it. Actually, if you think about it, when we teach a course, a class like this one, what we're doing is we're given a plant, which is basically not students, but learners that receive as inputs some kind of teaching activities and produce as outputs some, let's call it learning. So hang on with me. If we set some reference signals that are the so-called intended learning outcomes, you must have noticed in some of the classes, professors come up and say, okay, today's intended learning outcomes are this, this, and that, right? So the ILOs, those represent the reference signal. That is, of course, the output of this whole business is that people learn. So the intended learning outcome has to be of the same nature of the Y. The reference has to be compared to the Y. So the intended learning outcomes are compared to something which is, well, we have to measure learning somehow. Now that's the ugly part. That's when we have the exams. But really, we shouldn't be talking about evaluation. We should be talking about assessment tools for learning. And in fact, you will notice that from next semester, ETH has introduced the policies for continuous learning assessment. This means that throughout the course, every course that is given, we will have to come up with ways to actually assess your learning on a more periodic basis so that this loop can actually work in a more efficient way instead of having like only one measurement point every year. We get one measurement point every week, basically. We get the assessment tools that give us some measured learning, if you want, that we then go and compare with the intended learning outcomes. And the whole point, the whole challenge for those who are sitting on this other side is coming up with the controller, right? With some teaching activities, basically, a teaching activity planner or something like that. And these can be the lectures, can be the exercises, can be the hardware stuff sometimes, or any other sort of thing. So my bottom line here is saying that if you don't provide some sort of feedback and provide us a measurement of how well this is going, there's no way in the world we can do our better job. So there's roughly 400 students left in this course. Only 130 of you have filled up the course assessment. So it's important, do it now. I'll give you 5 minutes to actually go online and fill up the assessment course for the course of Control Systems 1. Please do it. It's important. It's important for the course. It's important for us. And yeah, what typically happens is the people who provide the feedback are only the very happy or the very unhappy. And this creates sort of a skewed way of evaluating the course. So it would be great if all of you that are mildly unhappy or mildly happy about the course would still pitch in that extra measurement point. So I'm not joking. Please, I'm sure you know how to do it better than I. So go on your assessment thing, and we've got 5 minutes to do so. So I'll give you up to 10:25. And I prepared some additional feedback sheets. You can find a link there, especially for the work and lectures of Dr. Musavi. Yes? Oh. A mistake, I'll fix it. It's a Google Sheet, but give me a second and I'll fix that. Okay, so it is not set to collect any personal information, so we're not recording your emails. I think you have to log in because there's I put it such that each of you can only provide one feedback. You can't answer this thing multiple times. So you'll need an ID, basically your Google account, to access the sheet, but then so you can see the collect email address thing is deactivated. It's completely anonymous. So. All of you that have not filled up these sheets already should be doing it now. And if you have already done it, then you should be filling up the one for Shima. I don't see all of you busy in doing something. So do I need to start walking through the desks and like checking you? No. Okay. We had enough time, we can proceed. So we're finally at the part of the course where we have basically gathered the sufficient tools to start doing some fun stuff. So at the very beginning of the course, we started becoming comfortable with this concepts of systems, of how control systems define systems, relates them to each other. We have started introducing a number of important tools like transfer functions to understand what is the steady state relationship between inputs and outputs, and different geometrical methods to evaluate important characteristics given a controller and given a plant of what happens in when the feedback loop is closed. We saw the root locus method that showed us how the poles of the closed loop system moved around as a function of a proportional gain of a controller. We saw the Nyquist plot that showed us through this weird Nyquist criterion that involved encirclements of some critical points if the system was not stable. And from the Nyquist plot, we saw even how to measure interesting parameters defining robustness, like the margins of gain and phase. And we looked at the Bode plots, which are ways to represent the frequency response of a system. And again, we saw in the Bode plots where to look at to find these important margins that determine robustness criteria. Then we moved forward and said, okay, but now we have tools for analysis, so we can actually tell what's going on if we're giving a controller and a plant. How do we do the opposite thing, right? So how do we actually do what we've set forth to do from the beginning of the course, that is design a controller in order to meet the particular specifications, no? And so we said many times, and it's the most important thing, that, well, when we design a controller, really the first most important thing you want to do is guarantee stability of the closed loop system, because otherwise things break, they blow up, they break down. Then once you have stability might not be enough. The mathematical definition of stability says, okay, things go towards some equilibrium, right? Okay, sure, but that equilibrium could be reached in infinite time. It could be an oscillation that depends on the system we're talking about. It could not be performant enough. So we talked about a number of performance specifications, both in the time domain and the frequency domain. And we said, well, look, suppose that we have a second order system. This is a system that has a transfer function defined by, let's say, has two poles or a state space of dimension 2. And we said, well, if we have the second order system, we can define some interesting time domain performances. For example, the steady state error. And we saw that depending on the numbers of poles in 0 of the open loop transfer function of the system, so the multiplication, basically the plant and the controller, versus the type of input that was sent into the system, that is the order of the ramp. If it's a unit signal, if it's a unit step input, well, then that's a ramp of order 0. If it's a line, it's ramp of order 1, and so on. We could see that by comparing the number of the poles in zero of the open loop and the order of the ramp, we could have either no steady state error or a finite steady state error or a diverging steady state error. Then we saw some time domain performance specifications in the transient. So things like the overshoot, the transient time, the settling time, things like this, always defined for second order systems. And we're like, okay, but second order systems are kind of, a small little bit of things, but we saw that we can always, not always, but most of the times we can approximate the behavior of a higher order system by choosing the dominant poles, and that basically tells us that we can look at the first or second order system simplification. So once we have defined these performance in the time domain, we said, okay, and this was actually something we will repeat today because I did very quickly at the last 10 minutes of a couple of lessons ago, and it deserves a little bit more attention. We defined the frequency domain specifications, and it's arguably, one could say that this frequency domain specification, obstacles and stuff is fundamentally the most important thing in control systems. Some would argue that this is your first control systems class today because we're going to look at how to design things in the frequency domain directly through techniques that are called loop shaping. And the last class you saw something called PID, proportional integrated derivative control, which is without a doubt the most successful control approach of all times because it's simple, it's intuitive, it's easy peasy to implement, and it's you can tweak your way out of it. You don't even need a model of the plant to actually get it to work, and it's successful. It's used today pretty much all over you go, wherever you go. And we'll see that loop shaping is basically a generalized version of PID, or at least PID is a particular case of loop shaping. So what is for PID? Just to do a quick recap, well, remember we've got a plant that we want to control. The plant has an input, U, has an output, Y, and the output might or not have some noise that acts on it. Well, at the moment we can pretend not. And then we've got some reference signal, which is something we would like the Y to follow. So we compare the reference signal and the measurement of the Y or the output directly to produce something that we call the tracking error. And then we have to decide a controller, right? Something to put in here. So something that is nothing but a decision-making process between a measurement of how well we're doing in the form of tracking error and the actual inputs that will have to go to the plant to hopefully compensate for this tracking error. And so PID says, well, look, just take the error, this difference between the reference and the Y, and then basically create the input signal to the plant as the sum of three components, where the first one is just, so I'll draw it here like a block diagram, the equations are below. The first one is just like multiply is a proportional term, proportional to the tracking error. So we just multiply the tracking error by a number. The second component is something that is proportional to the derivative of the tracking error. So what we do is we say, okay, let's multiply by KD, and let's take the derivative in time of the error that comes in. And the third part is proportional to the integral of the error. Let's just put it like this. Okay? And this generates a control law that has these three terms, which can be expressed in the frequency domain like this, but just remembering that integration in the Laplace domain is just a division by S, and derivation is just a multiplication by S. So you saw that this was a very effective strategy, and I will notice that it is important to see that this is an output feedback control strategy. You see the control input is proportional to the error, which is a function of the system's output. And I stress the word output as opposed to the system states, which is we mentioned throughout the course that the states contain a lot of information about the system, and if we know the states, then we can do some pole placement, not the ideal control, but we'll see this later on. So in summary, last class you saw that the proportional control terms help in decreasing the steady state error. You remember that when you had the same number of poles and zeros of your open loop part of the system and the same number of poles and zeros with respect to the order of the ramp, you get a finite error, not a finite steady state error, and that steady state error is inversely proportional to the gain. So increasing the gain decreases the steady state error. And you saw that proportional control has these characteristics. It increases the closed loop bandwidth. At the same time, of course, it increases sensitivity to noise. And it reduces the margins for higher order systems. But even with the proportional part that can stabilize a system and provide some sort of decent performances, still it cannot take care of the steady state error, as in removing steady state error. As you increase the proportional gain, you will reduce the steady state error, but always have it, right? And therefore, we saw that, well, if we add an integral part, something that you can imagine the integral part as something that keeps track of the history, right, of the past, and therefore, by keeping track of history of the error, one can compensate if there is a constant tracking error. Well, that constant tracking error will remain in memory, and eventually the controller will do something about it. So, adding an integral part to the control, well, tends to make the transient response worse because you're keeping track of a history, but at the same time, it helps to achieve better zero steady state errors. And the derivative control instead had this property of, you can imagine it as something that helps predict the future, so to speak. It helps helps the controller keep into account what's going to happen at the next step. So typically adding a derivative part to the controller reduces the overshoot because somehow the controller knows that the signal is about to get where it needs to be. Improves stability margins, but has this very ugly property that makes it really difficult to use in practice, that derivatives amplify noise. So every time you are dealing with a real system, every time you have a real practical system, the output is always something you measure. Every time you measure things, you introduce noise. Noise, you cannot take derivatives of a noisy signal because you'll have stuff that goes from plus minus infinity all over the place. So every time you use a derivative part for a controller, thread with care. You have to make sure you do some pre-processing of the measurement in order to make it acceptable. So we saw about what each component of the PID controller does, but we really didn't talk about how to tune it. Now that is like how to find the coefficients Ki, Kp, Kd in order to achieve some specific performances. And the truth is that there are many, many, many different methods to go about this. But the most important ones are the so-called synthesis through attempts, which is a fancy way to say tweak until death. So you just hire someone, you put it there that plays with the knobs forever until the performances are better, because you can always find the better combinations of the three coefficients that gives you a slightly better performance. Or you use numerical tools. MATLAB, CISO Toolbox is a good one. There are many other ones to help with the process. And it's worth noticing that, well, when you play with the knobs, you don't even need to have a model of the system in order for things to work. This is a huge thing. So not always, so we are always assuming you have a transfer function, you know a relationship between input and output, you have a model of the system. But suppose you could do all of this even without a model of the system. Well, wouldn't that be nice, right? And you actually can do it by just tweaking the knobs of the PID controller by hand. And there are, of course, more advanced methods to do this. We will not get into any advanced method for doing PID tuning. I will just mention, for historical purposes, the Ziegler-Nichols approach, which is just basically a way to, it's based on heuristics, so a lot of experience, basically. And it's a method that says, well, first play around with the proportional part of the controller, which is definitely the one that brings the biggest contribution, let's say, to the performance of the closed loop system, and tweak it until you find a critical point where your output is at oscillation, is a steady state oscillation. Then once you find that critical point, just measure the period of the oscillation, and I'll provide you a table with crazy numbers. Just trust me, plug in these numbers and you find the rest. That's what the Ziegler-Nichols approach is. So we'll look at this in a second, but another way of doing it is always saying, okay, well, we saw what was the influence of zeros on poles in a transfer function. Like if you look at the root locus, for example, we saw that given the numbers of zeros on poles in the system, you get different shapes of the root locus. Therefore, if you increase the k, things happen, and closed loop poles move in the imaginary plane, right? Well, you can always imagine a PID controller as simply, you just rewrite it by using this expression here. You just rewrite it as 2 zeros and a pole. And this basically allows you to just proceed and saying, okay, well, all I'm really doing by doing PID is adding 2 zeros and a pole in 0. So where should I put the zeros of my system? You can choose them based on performance criteria like the damping or the natural frequency, and then derive the PID coefficients from other characteristics. So the Ziegler-Nichols rules basically says, okay, imagine your system to have that kind of form. And we haven't really talked about it in class. Maybe we will touch upon it next class, maybe not. We'll do them directly in control systems too. That term e at the minus ts represents a delay. I'll just leave it at that. But so suppose you have a delayed first order plant. Well, the approach here is saying just start with a proportional controller. Feedback, measure dy, compare it with your reference, multiply it by a number, use that as the input to the signal, change this number, and continue measuring the output until you see the output having a steady state oscillation. At that point, you will call the proportional gain that you used a critical number, the critical gain. And you will measure the oscillation period of your output, and this table provides you then what are good starting points for the other coefficients in order to obtain decent performances. Again, I mentioned this for historical reasons. You might use it or not in your professional life as a starting point, maybe for something else. This is not a solution to PID tuning, it's just a way to get a starting, let's say an initial condition that makes some sense. So this class is going to be about loop shaping. As I mentioned before, loop shaping is a more general, let's say, approach to control systems, and arguably the most important thing there is to do. Classical controls is all about loop shaping. And to understand why loop shaping is relevant, we will have to carefully go through this few fundamental concepts that we have mentioned a few times, but it's always, repetita iuvant, it's good to repeat them. So we looked at this point, you are familiar with the closed loop negative feedback scheme. And we're familiar with the concept of transfer function, which is a mapping between the steady state values of an input and an output, right? The way we introduced it is always saying, well, the input is u, the output is y, as the input and output to the plant we want to control. Or really, input and outputs are input and outputs of any block or sequence of blocks. So in our closed loop diagram, we have a bunch of different signals. We have the reference, the error, the inputs, disturbances, noises. Keep in mind that disturbances are represented like this in this diagram, but could very easily represented disturbances at the input instead of disturbances at the output. You'll find the different schemes, different books will have different, let's say, conventions, but both, of course, are legitimate, and actually it makes sense to have a disturbance at the input as well. But if we just assume this scheme, well, now, every pair of signals you choose will have its own transfer function, right? So if we patiently crank through the math, as we did once already, you can see that the relationship, the transfer function between the reference signal that we consider as an input to the whole feedback loop, right? If you imagine this whole feedback loop here to be just one big block, Well, what are the inputs and the outputs of this block? Well, the inputs of this block are the reference signal, the disturbances, and the noises, which are often called the exogenous signals. There is everything that is just thrown at your system, right? We get to choose one, we don't get to choose the others, but this is what is the input to our feedback problem. And the output is typically the output of the system, or actually even better, it's a measured version of the output. But anyways, so if we choose any pair of signals, we got a transfer function. Now, the transfer function, there's a few transfer functions that are really, really important. The sensitivity and the complementary sensitivity functions. And they're called the sensitivity and complementary sensitivity because they add up to 1 at every value of S, which is this part here. So, okay, what are they? How do they come out? Well, they come out by simply writing the math here. Y is equal, now forget D and forget N for now. Y is equal to PU, which is equal to PCE. E is equal to R minus Y. You just plug this in, you get the sensitivity function, okay? It's like a two-passage thing. This kind of math you should become very, very familiar with. You should be able to do it in like if you're waking in the middle of the night. And do it with care. Don't remember things by heart, because as soon as we step a little bit forward and make this slightly more complicated, for example, in control systems too, we will talk about multi-input, multi-output signal systems, then all the order in which you do things becomes very important, because transfer functions are now transfer matrices. Anyways, we'll get to that, but just become familiar with this math. Do it if you've never done it before on your own. So why are these two transfer functions relevant? Well, look, the transfer function between the reference and the error signal means, well, if I send as an input a reference, remember the reference is what you would like the system to actually do at the end, right? So if I send in a crazy reference, because that represents something that allows me to, I don't know, fly my airplane well, drive my car efficiently, or make a lot of money on the financial market, you want to make sure that the Y tracks the reference, because that's the objective here. No? So if this transfer function represents the map between the two, well, if it's equal to 0 every time, it means that the error is 0. So for every reference, we've got an error that is 0, right? Because E of S would be equal to S of S times R of S. So for all R of S, if this is very, very small, or to the limit 0, well, we would get a 0 steady state error for any choice of reference signal. That would be perfect, right? Because it would be perfect tracking. 0 tracking error means that R is equal to Y at all times, right? At the same time, this transfer function represents even the relationship between the disturbance and the error, right? So disturbances are something we cannot control, something that is some signals that add up to, for example, our outputs or our inputs, and they are a disturbance, as the name suggests. And again, we would like the effect of disturbances on the tracking error to be very small, ideally 0. This is what we call disturbance rejection. And so these transfer functions are described by the sensitivity function that has this shape. Now, if you just look at it for a second, remember that L of S is nothing but P times C. If you want these to be small, we want these to be small, right? And we will see later how this is possible. On the other side, for example, this complementary sensitivity function represents the ratio, the relationship between the noise and the output. No? So it's always good to have very little effect of noise on the output, because otherwise the noise is fed back into the loop and it generates problems. And this is given by doing let's say a good control system that allows noise attenuation, that is minimizing the effect of noise, is a system that has a small complementary sensitivity function. So ideally, of course, we would like a control system that rejects disturbances completely, attenuates noises completely, has perfect tracking, and is perfectly robust, right? That's like in the perfect world. Clearly, remember this one golden rule that applies to all all things in science, which is there is no free lunch, right? So you cannot get everything you want. In general in life, and in particular in control systems, there's no way to achieve all these objectives at once. There's trade-offs that need to be done. And we can see these trade-offs, for example, by just looking at the fact that L plus T, S plus T must be 1 at every point in frequency, for every S. So if you choose an S and you want good disturbance rejection, you need to have low S. But if, low magnitude of the sensitivity function. But if this is very low, the sum of this and the complementary sensitivity must be 1, so the other must be very big, right? There's no way it's like two ends of the same rope. You can't just pull them both down. One goes up, one goes down. So how are we gonna figure this out? And this is the problem of control systems. Fundamentally, it's the biggest challenge in designing a controller. And so the way we fix this is by saying, okay, look, typically disturbances and commands, in this case, this is wrong terminology, this is reference commands, it's actually an R, are low frequency, are typically low frequency. Low frequency means anything up to 10 hertz. Of course, this maybe 5, 6, up to 10 hertz. And noises are typically something that have a much higher frequency content, are things that are like measurement, like the noise you find in electronics or things like this that are above 100 hertz. So the way the conundrum between trying to achieve all the different performances, although there's this constraint of the complementary sensitivity and the sensitivity function, is solved by doing a division in frequency. So we say, well, we want to satisfy the good disturbance rejection and good tracking at relatively low frequencies, because that's where typically these signals come out. It's very unusual. If you're driving a car down the road on the highway, you'll give an input to the car, you'll change the steering wheel with relatively low frequency. If you just start moving the steering wheel back and forth at 200 hertz, nothing is gonna happen. All those vibrations are gonna be absorbed by all the mechanical components. The system will not respond to high frequency references or high frequency inputs. And on the other side, if we want to reject the disturbance noises, well, the noises come at high frequencies. At high frequencies, we don't care about the following references because those the physical systems wouldn't react to them anyways. So we worry about the noise rejection part only at high frequencies. So in order to really now, are there any questions about this? Because this is really important. These are like the fundamental steps. There's 3 or 4 passages that are the ones we're doing now that lead to a very important conclusion. That's going to be like, there's 4 things you want to learn from this course: stability, performance, and robustness. And then the 4th one is remember this plot, basically. So are there any questions, comments, or doubts on this up to now? No. Okay, so remember what we did up to now. Every time we wanted to derive some conclusion on the closed loop, we always said, okay, but we're lazy, right? Everybody is lazy. So let's figure out a way to do so by only focusing on the open loop part. So given a plant, given a controller, we developed a bunch of different graphical methods to come up and say what were the performances of the closed loop system. So the question we ask ourselves now is, can we just re-represent these insights that we've gained on sensitivity and closed loop sensitivity and complementary sensitivity function on the open loop transfer function L directly, so that, again, we can focus only on the C times P and forget basically about everything else, but still guarantee good closed loop properties? And of course, the answer is yes, right? So we said that for good command tracking and disturbance rejection, we said we want the sensitivity function to be low. Now, what does it mean, a sensitivity function to be low? Always remember that when you talk about complex numbers, small, and there's always magnitudes and phases, right? So small in this case is the magnitude. So it means we want this term here to be very small. So if you look at it, well, this is 1 over 1 plus L. Well, if we want S to be small, L needs to be big, right? If L is infinity, S goes to 0. So this is the first big lesson. We want L to be big at low frequencies to have a small sensitivity function, which means good reference tracking and good disturbance rejection. So the way this is typically written is not just by saying, okay, so what does it mean as to be small, right? So small is always with respect to something. So depending on the specifications that are given, for example, say that someone comes to you and says, I would like you to design a controller that has 0 steady state error for I don't know, unit inputs, and then a constant steady state error for ramps. It's like, okay, fantastic. So, but that constant steady state error needs to be 1%, 2%, n%, whatever it is, okay? Not more than that. So this is something that can be written directly in this form. So basically that percentage, if you want, ends up, of course you can make it even more complicated. You can define what is called the low frequency obstacle, or if you want a weighting function, this W1. And typically S is small is written in the form S times something is less than 1. And that something is user defined and it's a specification criteria basically. So by just following simple math, this turns out that the low frequency disturbance rejection and good tracking performances of the closed loop can be simply represented by looking at the open loop transfer function, L, and saying it must be bigger than some value. So we can imagine this W1 as a low frequency obstacle on the magnitude Bode plot. Remember that on the Bode plot, we plot the frequency response of the open loop transfer function. We go and do the same thing for the noise rejection. We will see that it turns out that the conclusion is that we want for the complementary sensitivity function to be small at high frequency, we want L to be small at high frequency. And again, this is typically represented as L times some other function. It has to be bigger than 1. Therefore, L needs to be smaller than a high frequency obstacle. And this is represented in this plot here, where we have this obstacle here that is a way to characterize specifications, for example, on the steady state error. This obstacle here is something that is defined in a way to characterize performances in terms of noise attenuation. And then what's going on in the middle, right? So to see what's going on in the middle, we have to introduce a concept. The concept of, it's very important, it's the bandwidth of the closed loop system. So the bandwidth of the closed loop system is defined pretty much arbitrarily for historical reasons as the range of frequencies. So it's basically from 0 to some frequency. So you say typically the bandwidth is that high number, that omega, at which the magnitude of the complementary sensitivity function is bigger than this number, which is roughly 0.7, okay? And one could argue why this is the case. We can talk about it later, but this basically means that this basically means that the output can track commands within some sort of accuracy, within some sort of percentage, okay? So, but this closed loop bandwidth, actually, it would be nice if the bandwidth is related to the closed loop system, but again, we like everything expressed as a function of the open loop part of the branch because it makes our life easier. So you can imagine that, okay, suppose that, so do you remember we introduced the crossover frequency, right? The crossover frequency was the value of the frequency at which the open loop branch was a unit value, no, which the Bode plot crossed the 0 dB part. And if we just imagine to take an open loop transfer function of magnitude 1, no, magnitude 1 means that if we look at the Bode plot, this is the real part, this is the imaginary part, it means we are on the unit circle, right? And we assume the phase margin is 90 degrees. So we are at this point down here. Then L of j omega c is equal to minus j. And this means that if you do the magnitude of t of j omega, that is the magnitude of minus j over 1 minus j, you'll see that it is exactly 1 over root of 2. So this is just to say that we can approximate, if we assume that we have a phase margin of 90 degrees, because remember that the phase margin is defined as the angle of where the Bode plot, where the Nyquist plot crosses the unit circle and the critical point here. we can basically say that the bandwidth of the closed loop system, under some assumptions which make our life good, I mean 90 degrees margin of phase is a big margin of phase, it's something that means good robustness of the system, then we can say that the closed loop crossover bandwidth is basically the same as the open loop crossover frequency. So, which is this value here. This is the L of j omega, actually the magnitude of it, of course, represented in a logarithmic plane. This is the Bode plot, the magnitude plot of the Bode diagrams. And so the first part is all about disturbances. The second part, the high frequency part, is about noises. And the intersection here, that is the crossover frequency, determines the bandwidth of the signal, which is that frequency range. It is a measurement of two things. The first one is how, again, it's a measurement of how well we can track reference signals in the sense of, imagine always frequency content as a variation, speed of variation. So if I have a high frequency signal, what does it mean? It means a sinusoid at high frequency. So something that can vary very quickly in time. So having a high closed loop bandwidth means that the system is able to keep track of reference signals that vary very quickly. One other last very important actually idea we have not talked about formally in this course, we kind of hand-waved it, and we will talk about it in control systems too, is the slope at which the magnitude of the Bode plot intersects the 0 dB line. And that's because it's related to the phase margin of the system. I mean, the intuitive way of understanding it is, well, we saw that we could approximate the closed loop bandwidth with the crossover frequency by doing that assumption on the 90 degrees of the margin of phase, right? So the idea is that this slope determines the margin of phase. So it's related to the phase of the system, let's put it like this, and therefore influences the margin of phase. So a good rule of thumb is having this, slope to be around 20 dBs per decade when it crosses the 0 dB line. And the idea is as flat as possible. Of course, it can't be totally flat, otherwise there's no crossing the line. Okay, we will continue later with how do we actually get this to work. Okay, so you got 2 extra minutes. Can you believe that? So I'll get these 2 extra minutes at the end. Okay, before we proceed, please take a seat. Before we proceed, does anybody have something to say about this diagram? Questions to ask, things you do not understand, things you disagree with me? Speak now or forever hold your peace. It's your opportunity. No? Good. So you're convinced that that's actually, yes, you have something to say? You're like Superman. Okay, well, then, is this still working? Yes. Okay, then once we agree that this becomes the objective of our whole game of designing a controller, and we should agree to that because you didn't answer questions, you didn't ask for questions, really, it becomes a computer game now if you want. Imagine to start from the top left corner here, okay? All you have to do is you need to drive your car down, which is your magnitude of the open loop transfer function, down in this obstacle course. Somebody comes to you and says, you have to make sure you avoid this big low frequency obstacle. So all you have to do is start adding poles and zeros, adding terms to your controller, such that you steer this open loop magnitude of the open loop transfer function to be above that low frequency obstacle in order to have good disturbance rejection and reference tracking. You want to make sure that then as you pass your obstacle, you continue going, then you want to make sure you cross the 0 dB line so you want to have a crossover frequency that is pretty much the bandwidth of the closed loop system that satisfies other requirements. So it has to be typically as big as possible, but depends on the requirements. but you want to make sure that you cross it at a gentle slope. And then as soon as you cross this gentle slope, you have to immediately steer back again in order to avoid the high frequency obstacle that is typically some other big function that is provided to you in terms of specifications on the noise attenuation. Somebody comes to you and says, we want to make sure that the noise doesn't have an effect of more than 3% on the output measurement. Okay, so that's how you write down that W2. And so if you remember the lesson on Bode diagrams, we remember, like, we looked at a term at the time, right? We saw, okay, what happens if you got the constants, the S's, the first order terms, and so on. And basically, you will remember that if we added 0 in the terms of a 1 plus tau S term, what we're doing is we are steering the open loop transfer function up. If we add a pole, we're steering it down. So basically, you can drive your car of the open loop transfer function just adding poles and zeros at the right frequencies. Now, this is the general idea, and if you want, we could stop here, and if you go and look back at the at the specifications lesson, and you see how to relate all those values we saw in the time domain and the frequency domain to these two obstacles. Given these obstacles, it really only boils down to adding poles and zeros in the right places to avoid the obstacles and crossing the 0 dB line in the right way at the right spot. So, but there is a better, more systematic way of doing this, of course, right? So, the way we think about this, up to now, we thought about using a proportional controller, right? Was the thing that we looked at most. And we looked at PID as well, but the proportional controller is basically a static controller. It's a controller that whatever it is, in the sense whatever the frequency, let's say part of the frequency, at any frequency and at every point in time, the controller does always the same thing. It takes the error, multiplies it by a number, right? Always the same number. So that works, it's nice, it's cool, but of course has its own limitations. And if you remember, what happens when you take a transfer function when you're doing the Bode diagrams and you multiply it by a number. You add a constant gain. Suppose it's a positive number. In the Bode diagram, what happens on the magnitude? Yes, sir. You just shift it upwards, right? So multiplying by a gain, it's nothing but translating upwards this whole thing. So now that we have an idea of what are the obstacles of this game, is it always good to just crank up the proportional gain? Well, yes, in the sense that you're pushing up the low frequency, so we're avoiding the low frequency obstacles. That's probably a good thing. We're increasing the crossover frequency, increasing the bandwidth of the system, so that might be a good thing. But at the same time, we are increasing even the effect of noise on the system, so that is a bad thing. So it's not always, we might just translate this curve up enough to hit the high frequency obstacle, and that means the controller doesn't satisfy the requirements anymore. So that's where we can now step in and say, okay, let's use some form of controller that's a little bit more sophisticated. Let's say a dynamic compensator, they call, I don't know who they is, but they're called. So, and typically, so what is a dynamic compensator is a controller that is a transfer function on its own. So basically, we can say at the end of this, the way we're going is, let's just think of elements of the controller as transfer functions of the form a pole over a 0, okay? And if each one of these terms is, let's call it an Ri of S, where I is, depending how many you want, 1, 2, 3, n, or actually maybe Q is a better number because n is another thing, then we are about to come up with a design procedure such that your final controller, C of S, will be nothing but the multiplication of a bunch of these elements, which are these dynamic compensators. In particular, they're called lead or lag networks, depending on what is the relative position of the pole and the 0 in this ratio of poles and zeros. We'll look at in detail what changes when you change the relative position. And then, so you say, okay, I'll add 1, 2, 3 n of these lead lag networks, depending on how complicated the plant and the specifications are. And then I'll add a gain just to fix the last details. and a bunch of poles in 0. Why the bunch of poles and zeros? This we should already all understand why. Because the poles and zeros immediately allow us to satisfy requirements on the steady state. So if somebody comes to you and says, hey, I want zero steady state error to an M order input. So there's no need to think about it. The only way you can achieve that is that your open loop transfer function, that is plant times controller, has M+1 poles and 0. So check how many the plant already has. If it doesn't have any, you need to add M+1 poles and 0 in the controller. No way around it, okay? So this is typically the easiest part when you get in the design of a controller. First, add as many poles and zeros as you need to satisfy the steady state requirements. Then you start looking at things that are a little bit more tricky. So, as we said, the proportional control term, what it does is it translates the whole thing up, right? So we can skip this slide because we understood already what are the trade-offs there. If you translate the whole magnitude of the open loop transfer function up, you get a higher crossover frequency. And there's a bandwidth of the closed loop system. We reduce the steady state error. This is something we know from previous classes. And well, the downside is, of course, that we might simply go and hit the high frequency obstacle, which is something that would break specifications. But the interesting part here are these lead and lag networks. So let's look, or compensators. So let's look at what they are. So what is a lead compensator? A lead compensator is a transfer function that is a ratio of a pole and a 0. And if you remember the lesson on Bode diagrams, if this is the magnitude of, and the phase, so this is the magnitude and this is the phase, and this is omega. So when we add the 0, what we are doing is we are giving a contribution to, so at 0 we said, okay, look at the terms 1 plus tau s with tau being bigger than 0. Now we did all our math of our different studies. A 0 would add a phase contribution that is something like, a magnitude contribution that is something like this. Well, and this point here is the breakout point, that is 1 over A in this case, because you see that we called, it would be 1 over tau. And so actually this is A, not 1 over A, so my apologies. And if this is A, the phase contribution would be something that goes from 0 to 90 degrees. And it starts at 1 decade before. Remember, we did the asymptotic approximations, right? So instead of going and writing exactly what happened, we said, well, let's just say, what happens if it's very small, very big, the frequency with respect to the critical point. This is 0.1A. We had something that went up like this to 90 degrees, and this point here was a decade above A. Now, this is the contribution from a 0. If you do the same thing from a pole, you get basically the same thing flipped over, right? So, well, now if we put the B at the same point of A, you would get exactly the specular thing, right? So if you sum them up, because that's the final contribution, the nice thing about Bode diagrams, you can just sum up the contributions of each term, and you get what is the final frequency domain response of this controller part. Well, if we had A equal to B, they would just cancel out. Of course, everything cancels out, and what's the point, right? But now what happens if we move B and we make it bigger than A, okay? So this is the case of the lead compensator. A lead compensator is a ratio of a pole and a 0 where the pole is bigger than a 0. Why? Because if we now suppose that B is bigger than A, then the pole would give this contribution here, right? For the magnitude, and for the phase, let's say that B is 1 decade higher than A, just to make it up, it could be any value higher. Then you would see that at 1 decade, it would do something like this, the phase contribution, right? No, not like this, actually. It would do something like this, where this value here is 10B, 1 decade above, right? And this value here is minus 90 degrees. So let's sum them up, and let's see what would be the contribution of the whole network, lead compensator element. So in this case, where B is much bigger than A, that is, it's at least a decade bigger than A, we would get something that up to here is 0, then increases with 20 dB per decades, and then gets compensated by the other part, so you get something like this, right? This is an example of the magnitude contribution of a lead element. For the phase one, instead, it's a 0, 0, 0, then it starts going up, and it stays at 90 degrees. It doesn't grow more than 90 degrees, right? So there's a cap there, and then it starts going back down. So basically, this goes to 0, starts going back down, and here it goes like this. Okay, this is if B is it's a decade bigger than A. Say the best case scenario in terms of phase contribution. So why do I say a best case scenario? Why is a phase contribution a good thing? So why are they called lead? Lead is the opposite of lag. What does lag mean? Lag means a delay in time. Okay, so in this context, a lag is something that provides a negative phase contribution. So when you have a term, we'll see it later, lag networks are done on purpose for this, that add a negative term contribution, that's adding a delay, it's a bad thing, and we try to compensate for that. So why is it a bad thing? It's a bad thing because you have to remember this concept of margins, very important, the margins of stability and the margin of phase, which represent the distance between, let's say, they're a measure of robustness, we said. And why was that? Because they represent the distance between your current situation and the critical point. That is the amount of things that can happen, if you want, in some measure before your system goes unstable. For example, what uncertainty can you have on the model of your plant before your controller designed for a nominal plant still works? So if you remember, the margin of phase was defined as the distance, the difference between minus 180 degrees and the actual phase of the system. If you remember the Bode diagrams, sorry, the Nyquist diagrams, if this was our system, then the margin of phase was defined as the angle at which your Nyquist plot hits the unit circle and the actual critical point, that is minus 180 degrees. If you were to rotate your whole Nyquist plot of that amount of the margin of phase, your Nyquist plot would hit the critical point, the system would go unstable, which is bad. So adding a positive phase at the right spot, at the crossover frequency, actually increases your phase margin. So lead is good. Adding positive phases is a good thing if they're added in the right spot. While on the other side, adding negative phases typically is something that at the wrong spot, that is at the crossover frequency, is something that reduces the phase margin, therefore pushes towards instability, which is a bad thing. So this is the situation for a lead compensator. And of course, one can play around with A and B, right? So you can play around with A and B, and what you notice is that, well, basically, this phase so the real reason for which lead compensators are used is to add phase. Okay, when you have a phase margin that is not big enough, you add a lead compensator so that you deform the open loop transfer function of your system just locally in the frequency domain. So the whole loop shaping techniques is all about going there with a chisel in the frequency domain and just adding little bumps and curves at the open loop transfer function so to navigate those obstacles. It's really, this lead and lag networks are just but kind of convenient ways to modify the magnitude and the phase of the open loop transfer function at only specific regions of the frequency regions, so that you can bend basically that obstacle course that we saw before and achieve the performance specifications that you want. But remember that a lead compensator basically can at most provide 90 degrees of phase increase, right? There's no way you can provide more. If you need to increase the phase of your system of 180 degrees, we'll probably need to put at least 2 of these, maybe more of these elements. Remember that we can, in theory, add as many as we want to the controller. Okay, so, well, where does the maximum increase happen? Well, the maximum increase happens at the midpoint between B and A. And the midpoint between B and A and the frequency domain, since we're writing this scale in a logarithmic way, it's actually the root of A over B. So how do you design a lead network? Well, that's tricky, and we'll talk about it. So let's see. The typical use of a lead compensator, again, is to increase the phase margin because it bumps up the phase, right? So how do you design it? Well, the biggest phase margin contribution comes at this point that is the geometrical midpoint between A and B, which is root of A times B. And of course, I mean, the whole point is adding a phase to the system, and it makes sense to do it at the crossover frequency because that's where you define the phase margin. So, well, the first thing you would do is make sure that root of A times B is equal to the desired crossover frequency because that's where you're gonna be adding your phase. And then how do you choose B and A? Well, what really matters in terms of phase is how distant they are. And we saw that basically if you put them at 1 decade distance, that is a big distance from each other, you already get the maximum phase contribution that you can get, which is 90 degrees, more or less. So the important thing is trying to make them symmetric with respect to the center point, right? Because otherwise the center point is no longer the center point. So how do you actually do it? Well, trial and error is a big thing, actually happens, especially nowadays with computer programs. You can easily just plot things with click, click, click. So you just play around with the numbers until you get satisfying performances. Of course, you start from educated guesses, which are the ones that we are talking about now. Well, if you just do geometrical considerations, you know that if B and A are a decade apart, you get 90 degrees. You know if B and A are exactly the same number, you get 0 phase increase. Well, then how are you going to choose it? So you're going to choose B over A, that is some number between 0 and 10. And it depends on how much phase margin you want to add. If you want to add, let's suppose there is a linear increase, that's not what happens, but it doesn't matter. You want to add 45 degrees, well, choose B over A to be 5, okay? This could be an educated guess to start from. It's not exact, but another way of doing it, which was actually the way I was taught when I was doing Control Systems 1 the first time. Apparently, it's no longer a thing now, but use tables. Somebody gives you the tables of the compensating networks, which is something every engineer should go around with, every control engineer should go around with. And once you have the tables, it becomes super easy and intuitive to figure out what the right values are, as we will see in an example. So what you do to design a lead compensator is you pick the root of A over B, and then you choose how distant they are to understand how much phase contribution, and then you just adjust the decay to fix the details. Let's see an example. Any questions, comments, or doubts on the lead compensators? The bottom line is just a pull over a 0. And you have to play around with the pull and 0 positions in order to get as much as possible of what you care about in a lead compensator, which is the increase in phase. And we saw that if they are 0, then you get 0 increase in phase, of course, because it simplifies to 1. If you get, they're a decade apart, you get 90 degrees, which is the maximum you can get out of one lead element. Okay, so typical example, somebody gives you a plant, here is your plant, okay? So for now, we are talking about open loop minimum phase and stable plants, okay? So they're the easy ones, let's say. If this were non-minimum phase, that is, had a 0 on the right-hand plane, or if it had unstable open loop poles, that is some pole on the right-hand plane, we would use an escamotage, a different method, which we'll talk about later on. But now let's just focus on the easy part. So somebody gives us a plant, and they come to us and say, hey, I want your desired bandwidth, and I want the bandwidth of the closed-loop system, because it's a bandwidth to be, whatever, 5 radians per second. And we want the phase margin to be bigger than 45 degrees. It's a typical value, okay? 90 degrees is really a good phase margin. More than 30 degrees, it's already acceptable. More than 45 degrees, it's a robust controller. Okay, so how do we proceed? Well, the first thing you do is you plot out this, right? So you remember your Bode diagrams, and you go and plot it out. Can you see it actually there? Yeah, right? And it's this blue curve here. Okay, so you say we want the crossover frequency to be, the bandwidth, that is the crossover frequency, to be at 5 radians per second. So we have to kind of go and check now where at 5 radians per second, what is the frequency, what is the phase of this existing plant, because maybe we already satisfied the requirements and we don't really need to do anything. So we need to go and look for 5. So this is 10 to the 0, 1 radian per second, 1, 2, 3, 4, 5. Remember, this is a logarithmic scale, so you count the ticks to have the linear increases. 5, so it means we are here, oops, here roughly. So what's this value? Well, this value is roughly, so what's the distance between here and minus 180? So that's the margin of phase at this, if the crossover frequency were to be the 5 radians per second. We see that the margin of phase here, it's roughly what? Roughly 20 degrees, something like that, okay? So that means that we're not satisfying our requirements. We need to increase the margin of phase of another 25 degrees at least. So, okay, so what do we do? Well, we have studied lead networks. We want to increase the margin of phase. We will design a lead network to deliver the appropriate margin of phase. So the first thing you do is you say, okay, well, we want this margin of phase, this phase contribution to happen at the desired crossover frequency, that is 5 radians per second. So I need to choose, remember that this is about finding A and B, because lead lad thing is S over A plus 1, S over B plus 1, which is equal B over A, S plus A over S plus B. It's all about finding A and B. And, well, we choose this to be the midpoint, remember, is where you get a maximum phase contribution. You choose it at root of A over B. Now we've got one constraint on our A and B, and then you have to choose the B over A. And here it's where the little bit, the ballparking, the eyeballing comes in, right? So because of considerations we did before, we said, well, let this B over A equals to, this is wrong, equal to 1. You get 0 degrees. At B over A equal to 10, you get 90 degrees. Well, 25 degrees might be somewhere like BA4. It doesn't really matter if you add a little bit more. Now, remember that the requirement says bigger than 45 degrees. It doesn't say it has to be exactly 45 degrees. If you do 56, it's still good, right? So you can start with this approximation. This brings us directly. So now we have two equations, two unknowns. You can find A and B right away. And for example, A equals 2.5 and B equals 10 are numbers that represent these two, that satisfy these two constraints. So at this point, what you do is you have your first element, your first R of S, and what you would do is now replot the Bode diagram of R of S times P of S and see what the situation is. So what we have done here is basically add contribution of phase, this bump that you see here, at the right spot, and the bump was big enough so that we got the at least 25 degrees that we needed. But at the same time, this is kind of the side effect of adding a lead network, is that we increased even the magnitude a little bit. Now you see that when you choose this frequency to add this big bump in phase, there's actually a magnitude price to pay. In this case, it's actually not something bad, because we needed to increase the magnitude of the system as well. But anyways, you plot this, so what you get is basically a system that now has the right bump in frequency, but the phase is probably going to be 0, 0, so it's going to be the same number up to here, and then in this region here you have a little bit of a phase increase, so it probably is something like this. This is R times P, okay? Now we go at 5 radians per second, which is here, and we see that we still don't satisfy the requirements on the desired bandwidth, right? Because the bandwidth at 5 radians per second means that the crossover frequency needs to happen at 5 radians per second. But if we look at this line, the crossover frequency is defined when this line crosses 0 dB, and we're always underneath the 0 dB line, which is here. So how do we fix that part? Well, we just crank up the proportional gain. We translate everything up of how much of exactly this quantity here. The quantity needed to bring the intersection of the open loop part, the open loop transfer function, to hit the 0 dB line so that the crossover frequency is the one that is specified. If you do the math, you get up 52 is the equivalent linear value. So, okay, you would say, yeah, but this is arts, it's not science. Like, I have to eyeball stuff, be creative. Now, as soon as things become a little bit more complicated, how do you do it? Well, somebody came up with, so if you just think about the lead or lad networks with a slightly different formulation, that is, the pole is represented as a number and the zero is represented, let's say, the item that has to be bigger or smaller. The pole or the zero is just represented as tau and tau over m, where m is a number bigger than 1. So if you just look at the lead network, which is the one we just studied, you see that basically we said the pole has to be bigger than the zero. No? So this means 0, A, and B like this. And if m is bigger than 1, then this condition is satisfied. So these are the graphs, the so-called tables, for the lead compensators. Okay? Remember that if you want to see a table of a lag compensator, just get exactly this one and you flip them over by the x-axis, okay? Because It's the lag compensator is exactly the same thing as a lead compensator, it's just flipped over. So what was the thing we had to do? We had to, how do you use these tables? Now this is kind of, let's look at them for a second. So magnitude and phase of the element, okay, of a lead element. The x-axis is a normalized frequency domain. It's a normalized frequency omega n, okay? And the relationship between omega n and your normal things is this one. Omega n equals omega times tau. So what we wanted to do? We wanted to add roughly, what was it, 25 degrees at 5 radians per second, right? That was the let's say, design challenge in order to meet the specifications that were required by whoever came to us and said this thing. So how do we proceed? So each one of these lines has a number on top of it. That represents m. So the first thing you do is, of course, you go and verify what are the margin of phase and the bandwidth of the current system. You compare them with the requirements. Now we know that we need to, what is the contribution needs to be added. In our case, we need to add 25 degrees and at 5 radians per second. So, well, which ones shall we choose? Well, at 5 radians per second, where is eventually where we want to add this thing, if this is, okay, I think I did a mistake here in the thing, but whatever. If this is the, okay, sorry, I'm getting confused here. So forget about it. First thing you do is choose the M, okay? So the M basically tells us what is the magnitude of a phase or magnitude contribution that you wanna insert. So we needed 25 degrees, right? So if we were to choose the lead network characterized by this curve here, we wouldn't really get enough because the peak of this curve is at 20 degrees. So we need at least 25. So let's go with the next one, with this curve here, or maybe even with the next one, so that we get a little bit more margin of phase. It's never bad to have a little bit more. So if you choose m equal 4, you can see that the peak of m equal 4 is roughly at 36 degrees, right? So it means that if we were to add that lead network, we could get at most a 36 degrees contribution. These different things are nothing but, m is nothing but a measure of the relative distance between B and A, as we saw it before. So if you get m to be very, very big, more than 10, you see that the phase contribution increases and goes up to 90. So we choose, for example, m equal 4. Now, m equal 4 tells us what is the contribution of the phase and magnitude at different values of this normalized frequency. So which contribution do you actually want to bring? In the sense, in our design, we wanted to add 35 degrees, right? So where is 35 degrees in this normalized scale? So what is the value of the frequency that we want to select on these tables because of design criteria? In this case, we chose m equal 4, which is, probably it's better if I just do it here. M equal 4, which is this line here. And we want to add roughly, what did we say, 35 degrees, so maybe this point here is a good one, okay? So this point here, and note, these are our considerations of design, so we know we have to add 35 degrees to get the desired margin of phase. So here we would have mn star, which is the point we select because of design criteria on these tables, to be equal to 2, right? Always remember 10 to the 0 is equal to 1. The next tick is one more in the near scale, so it's 2. So we chose m equal 4 and omega n star equal 2. This means that we're adding a lead network that is contributing plus 35 degrees and what? And unfortunately, as a side effect, we're adding, what is it, roughly 6 dBs to the magnitude, okay? But the only question we have not replied to up to now is, where are we adding this in the actual unnormalized frequency domain here? Now, so we wanted to add it at the desired band, at the desired crossover frequency, because that is where we want to satisfy the requirement. So in this equation here, you just plug into omega n, the point omega n star, which is selected by design. Omega is the point where you want this effect to be brought in the actual real platform. So this would be your desired bandwidth of the closed loop system. And tau is exactly the value you obtain by doing the ratio, and it's the value you'll plug in your lead network. So this is a way that is a little bit more systematic to actually select the M and tau to add the contributions that are necessary. And in fact, if you plug in M equals 4 and omega n star equal 2, you get pretty much the same result that we got in the example by ballparking it with A and B. Any questions on this? These are those kind of things that you need to practice, okay? Like these are like the logarithmic tables. It's like, I don't know, my grandfather used to do calculations by using logarithmic books, okay? Because you didn't have calculators. This is that kind of stuff. Like you go and you have the tables, you bring it with you, and you learn how to use them, and you design stuff. But they work, they're useful, and actually after you practice a little bit, you can do pretty precise loop shaping exercises of complicated things by hand, basically. Okay, moving on. What's a lag compensator? Once we understood the principle of the lead compensator, the lag compensator comes for free, because the lag compensator is just the opposite. What the lag compensator does is always has a ratio of a pole and a zero, but this time the pole is bigger than the zero. It's the opposite situation. You invert the relative position of the pole and the zero with respect to the previous example. So this is the phase and magnitude contribution, depending on where you choose pole and zero, of the lag compensator. So why is it called lag? Because now it has this ugly effect that it introduces a phase delay, a negative component to the phase. And that's a bad thing. Why? Because it reduces the margin of phase and therefore sends your system towards instability. So why do people in the world would want to use these lag elements, right? What's the point? Well, the point is that it adds a positive magnitude contribution at low frequencies. So you see, the magnitude is 0, that is 1. So if you multiply, you just get a big number. It's a relatively big number at low frequency and becomes very small at high frequency, okay? So it's a way to shape the magnitude of a part of your open loop transfer function at low frequencies while leaving unaffected the high frequencies. The price you pay is a phase delay. So the skill of the control system engineer while doing loop shaping is now to make sure that we are adding the right magnitude contribution at low frequencies to get better load, better disturbance attenuation or reference tracking, and trying to make the effect of this lag die off before the critical point, before the crossover frequency, where it's actually the only point where we go and measure the margin of phase, which is where we care the phase to be big enough. So typically, lag compensators are used, as I mentioned before, to increase the magnitude of the low frequency part. This means that we know from the frequency domain specification that means getting better disturbance rejection and reference tracking. And basically, the similar considerations to what happened before apply in the ballparking. And of course, what happens is that as a side effect, you get this phase lag that is not positive. So if we just look at the example of before, so now this is a typical example. Somebody comes to you and says, okay, this is your plant. Now I wanted these two kinds of specifications in terms of crossover frequency or closed loop bandwidth, and in terms of margin of phase, so in terms of robustness. Now I even want some specifications in terms of steady state error to a unit step, okay? So this is just a way of saying that the the magnitude of L at low frequency has to be bigger than a certain number. Because if we say that the error has to be less than 1%, if you go and do the calculations, it's 1 over 1 plus S of 0, no, 1 over 1 plus L of 0 has to be smaller than 101 or something like that. So the bottom line is we have to increase the magnitude of our plant. Now our plant became the modified plant from before because we added that first part of the controller already to satisfy the requirements that were asked for before. What we're doing is we're designing this controller as a multiplication of a bunch of lead lag elements, ones and zeros, and a K at the end. No? So we start now from here, which is the result of the previous example. And what we need to do is we need to increase the frequency, the magnitude at low frequencies while leaving unaltered, so without touching the crossover frequency and the phase at that frequency, because that was the design we did before. So if we were to go and modify that part, we would have to go back and start again. So the whole point here is trying to, so remember that for our previous design, the crossover frequency was here, which is 5 radians per second. Let's see if this is actually right. Well, this is 10 to the 0, 10 to the 0 means 1, 2, 3, 4, 5. Yeah, pretty much right. So at this frequency, we have a margin of phase, which is this distance here, which looks to be at least 50 degrees. So we're good. Consider one of these pieces as 45 degrees. So what's the challenge of the lag element? So here the trick is just placing the pole, which is the B part, which is the one that is at higher frequency. Let's double check if this is right. It's actually not. Placing the 0, which is the higher part. You want to place it in a point such that the phase lag does not affect the frequency region around the crossover frequency, because here is where the margin of phase is going to be calculated. So if we just choose these numbers here for A and B, what we're doing is adding the necessary magnitude contribution to the low frequencies, and we get this ugly dip in phase. But the dip in phase is okay because it dies off before the critical part that is the one that actually we care about in terms of margin of phase and the crossover frequency. So, of course, one can always do this in the same way through these tables. We need to increase the magnitude of 10 dBs while keeping the phase lag low as possible. So, well, in this case, look, we would have to probably choose an omega n star that is very high, so that the phase contribution is very slow, very small, and in comparison, the magnitude contribution is very high. So, yes. If you remember that the transfer function between the error, the tracking error, and the reference was given by the sensitivity function, right? If you remember 2 classes ago, we said, okay, what are the steady state errors? They're given by the Bode gain, which was S of 0, basically. So it's 0 frequency. So basically, your steady state error is given by 1 over 1 plus L of 0. So if you just say that the magnitude of that has to be, what is it? We said 1%. So 1% means that it has to be 1 over 100. And you flip over the equation and you get how much does the magnitude of L need to be to satisfy this constraint. You get that number in dBs. Okay, so it's like putting an obstacle at low frequency that is a constant, saying up to 6 hertz, you want to be like more than. So you have to start the design from the S, but then you flip it over to the L, as we saw in those slides in reverting the specifications to the open loop terms. So remember that every time you design lead networks, you always get something you want and you pay a price in the meantime. You get the phase contribution you want and you have to get, unfortunately, a part of the magnitude as well. Sometimes it's helpful, sometimes not. My bottom line is that there are many different solutions every time. It really depends on the specific exercise you are dealing with. But the general idea is you use lead-led networks to change locally the open loop transfer function. And you want to choose the elements you design, the lead and lag networks, such that that locally is good enough with respect to your specific exercise. In this case, locally for the lag network means that the phase contribution needs not to affect the crossover frequency. Okay, so what's a general procedure for designing, for doing loop shaping, which is itself a general control system design approach? You start from the low frequencies, very, very low frequencies. Start from left, okay? And what's the leftmost point in the frequency domain? It's omega equal to 0, okay? Omega equal to 0 is a steady state. as we discussed a moment ago. So first, the first thing you do is you deal with the specifications at steady state, which are typically given in the form of, I want the system to have 0 steady state error up to ramps of order m, and n%, 5% error for ramps of order m+1. So the first thing you do, you add how many poles and zeros you need to meet the type, to make the open loop transfer function have the same number of poles and zeros than the order of the system. Then, as you are proceeding in the frequency domain, you will basically crank up the gain in order to avoid the low frequency obstacle, sorry, start adding zeros and poles to steer the transfer function so that you avoid all the obstacles in the graph that we saw before. And if you remember that all of this that we're doing makes sense only have proper transfer functions. So you need to have the same, at worst case, the same degree at the numerator and the denominator of your combined controller and plant. You'll see that you will add the same numbers of poles and zeros. And one way of seeing that is the lead and lag networks that we just studied. Okay, thank you very much.